as Nathan said, my name is Paul Polsky. I'm with Caterpillar. Currently, I am in the Building Construction Products Division, where we are working on electrification of smaller construction equipment, including many of the systems that we sell to the Navy. Prior to this, I spent 8 years as the ground-based power systems application and installation expert for Caterpillar Defense, where I did a lot of work on State Department locations, radar installations, naval bases, and alike. And before that, I was the lead engineer for the Marine Auxiliary Power Systems new product introduction programs. So I've been doing different bits of this for quite a while. Now, today I'm going to take about 70 minutes to run through this, and for any given one of you, 90% of what I say is just going to be obvious and you remember it all from school. The problem is that the 10% is different for each one of you, and there's going to be a couple of things that while you're familiar with, I'm going to try to present them just a little bit different to help set you up for the more detailed information that's coming with the rest of the instructors throughout this week. So, brief math refresher. Biggest problem we got is that variables are inconsistent. You know that it's going to be V or E for voltage, A or I for amps. Usually we're consistent on R for ohms resistance, but then we got complex resistance also, which is Z, power factor, PF. Then we've got watts, either shown as W or P, which can be confusing because if we're also talking about work, we're using W for work. So you're going to have to, in any reference you pull up on the web, any reference that you pull up from books, you're going to have to look carefully at the context of what they're doing to understand which unit means what. Some of the standard formulas that you're going to run into over and over in this course: three-phase available power. This is how much power is actually coming out the end of the generator to allow you to run your equipment. Three-phase total power. This is the amount of power that'd be available if everything was synced up perfectly at unity power factor. Then we've got the part that isn't synced up, then that's the reactive power. And then, of course, the power factor is just the ratio between the two. All right, so electric current. We know that we got AC. We know that we've got DC. No big surprise there. The thing is, on DC, everyone just assumes it turns on and it runs at a straight current. If you remember from any of your lab classes, that is never the case. You've always got noise. Even though you have noise, it's still a DC current. In fact, the noise or an intentional motion on it can have your DC voltage go all the way down to 0, sit there a while and come back up, and it's still considered a DC current. For alternating current, what we're looking at is it has to cycle all the way back and forth. It's got to reach to a positive voltage. It's got to go back across and have a negative voltage. Now, most of the time when we do this, we think about sine waves, and that is the most common, and that's what you'll get out of any rotating piece of power generation equipment, such as a generator. However, it's not the only one. When you're looking now at a lot of systems that are going to be adding solar and other DC power supplies and try to make them AC, not all power converters are created equal, and you will get things that are not pure sine waves. In fact, in some cases, you'll even get just flat out square waves. That's still alternating current as long as the actual polarity that you measure at the wires coming out switches back and forth. All right, now the other problem we got is voltage, current, power, to be honest, are all instantaneous measurements. It's the amount of voltage you got at that instant, the amount of current you got at that instant, that gives you the amount of power you have at that instant. But we don't run around in the field carrying oscilloscopes. So we want some way to do our calculations and look at a simple gauge and tell what's going on. The problem is if you've got older equipment that they might not be showing what you expect. And when we want to talk about the voltage of a sine wave, there's multiple different things that can be shown. There is the peak voltage. So that's the highest voltage that it went to from zero. There is the average voltage, the peak to peak voltage. And then what's important here is the RMS voltage. Now, notice up here that RMS and average voltage don't match up. There is a difference between the two. So why do we use RMS for the most part nowadays? Well, RMS is the easiest way to equate AC and DC power. If you have 120 volt AC going into a pure resistance heating element, it'll have the same effect as 120 volt DC if you're measuring the AC at the RMS value. Now, for a pure sine wave, RMS is equal to 70.7 of the peak value of the wave. Now, most digital multimeters you get nowadays measure real voltage in RMS. However, that's not always the case. First of all, some of the really low-cost digital multimeters actually measure the peak voltage and then take 70.7% of that and put that on the screen. That is not true RMS. And the problem with that is that when you get into systems that are running off of converters from batteries or from solar panels, it's not giving you a pure sine wave. So that means those cheap voltage gauges, those cheap multimeters, are not giving you what you actually are expecting to see. The second problem, which you will run onto occasionally, especially if you have to work with coalition forces that aren't as well equipped as we are, is that at times you will run on to older analog multimeters. Now, some analog multimeters are true RMS. Some of them are estimated RMS, and a lot of them are average voltage because it was simpler back before the age of microchips to make a rectified and averaged meter than it was to make one that measures RMS. And the thing is, for a pure sine wave still, that average value is 63.6% of the peak instead of 70.7, which means you are reading a significantly different voltage, and that can screw up everything that you're hooking in through the rest of the system. So the point of this is make sure that you have a good true RMS multimeter, because anything else is going to have your values off. And especially if you're doing anything in field operations where you've got a large amount of resistance coming in from cabling and alike, that difference could be enough to affect the ability of the equipment at the far end to work properly. All right, now, period of a cycle. 60 hertz is used in the US, it's used in half of Japan, and it's used in different parts of Central America. Most of your work when you are at your facilities is going to be at 60 hertz. However, in deployment or working with other NATO forces or like, you're often going to have to deal with 50 hertz systems. And those of you that are working on radar systems or working on flight lines, you're also going to have to deal with 400 hertz systems. Now, between 60 and 50 hertz, is one better than the other? Not really. There are some trade-offs on it. There are a few things that the voltage and frequency version we use in the US has some advantages, and there's some places where the 50 hertz has advantage. And basically what's being used on the grid in different locations boils down to whether they bought their initial generators for the grid from the US or from Europe. Now, 400 hertz, we're going to see when we get into more about capacitance, inductance, and power factors, has a big advantage on keeping things light. And we'll get into that a bit more later. All right, pretty much everywhere that you're going to work is going to have three-phase power. The reason we do that is it takes at least 2 wires to do a single phase. It only takes 3 wires to make a delta configuration 3-phase power. So you've added 50% to the wire the weight of copper that you have to drag around, but you've added over 73% to the amount of power you can get out. Now, there are also 4-wire 3-phase connections called Y, and they are definitely important, especially in ground-based applications. And we will get into some of that and why you'd be using that throughout this course. The thing is, most everywhere you go, what you're going to start with is the utilities coming in on a 3-phase delta connection, because it's the cheapest way for them to get the max amount of power to you. And so you're going to have to be working from that delta connection to everything else that you're trying to do on the site if you're trying to do both your own power supply and power from the grid. So what's the difference then between the Y and the delta? Well, the difference between the Y and the delta, the main thing of it is having a neutral wire. Now, it's important to understand this neutral wire is not the same as a ground wire. It's not necessarily tied into the ground of the case of the equipment that you're working on. This is an important distinction to keep in mind because it means there actually can be a potential difference between the neutral and actual ground. Now, to take care of that, one single place in a ship or an installation has a connection between the neutral and ground, and you want it to be only one. Because keep in mind that no matter how good we make the wire, or how good a conductor we put in, there's some resistance in it. And if we have more than one connection between them, there's going to be a difference in potential at one of the connections compared to the other, which is going to cause a current flow. This is not a good thing. On a ship, it can actually erode away the hull of the ship. On land-based, you don't really have that issue, but you still have ground loops causing things like the cases around your equipment to be charged. So the first thing we want to bring up on safety is if you're working on live equipment, assume that even the case is energized until you can confirm that there is no potential difference between that frame that you're about to touch and the ground connection for that piece of equipment. And until someone's checked that that ground connection is matching the central ground connection, assume that it is hot. Okay. Now, on delta connections, while they can be completely free floating relative to the ground, like what you see in the center color picture, you notice that a typical installation, like what's shown on the right, has the B phase connected to ground. Now, the important thing when we talk about connection to ground, whether it's a Y or a delta, is that in a given facility, you want it in only one place. And this is going to become important when you are renting additional equipment or when you're doing an initial installation of equipment. Most suppliers of UL listed equipment include a connection between neutral and ground, or a connection between B phase and ground if they're selling it as a delta connection. However, in your whole facility, you want only one connection between those two. So you need to remove the extra cable. On the other hand, most stuff that is sent 50 hertz is designed to EU standards, and the EU standard says they don't have to include a ground strap anywhere, that you are supposed to be smart enough to pick the location in your facility, whether it's on one of the generators or whether it's on some transformer or something else, to connect neutral to ground or B phase to ground. So you have to pay attention, especially on deployment activities, because what you're getting might not necessarily be what you're used to. All right, so looking at 3-phase, this is what we see. We've got 3 different phases. Each of them is a third of a cycle out of phase with the other 2. This means that we get peaks more often. This means that if we are using something that runs all 3 of these phases, we never have a situation where the load itself is experiencing 0 volts or 0 amps. This is very beneficial in keeping a lot of things running a lot smoother. But we don't always need AC. A lot of the stuff still needs DC. And back when we first tried to do this, and still in some applications, we have to translate the power with something called a motor generator. And what that is quite literally an electric motor turning a generator. Now, this can be set up so that the generator is DC, in which case we are getting DC power out of the one end of it while we're putting AC into the generator on the other end. But what you're going to see it more for nowadays is where you're connecting together two different grids that are either at a different frequency or out of phase with each other. One of those things is going to occur. Examples of that are if you are working on a radar installation, the inner components of a radar installation, whether it's put in Hawaii or put in Dubai, are 400 hertz. All right, I got a note that someone's not seeing the screen or hearing the audio. Could someone else pipe in and say whether they're seeing it?
Yes, we're seeing everything. I'm seeing everything.
Okay. So other places you're going to see this, the radar installations, pretty much everything is 400 hertz in the radar installation itself. And the design within the installation is pretty much the same, whether it's being put in Hawaii on a 60 hertz setup or it's being put in Dubai onto a 50 hertz setup. There is enough power required there that a motor generator system is used to do the conversion to 400 hertz. Another place you'll see it is if you ever work more towards the center of the US is actually, mainland's actually broken into three grids: Eastern grid, Western grid, and Texas grid, because Texas always wants to be different. The reason for that is it takes time for electricity to get from one point to another, even though it's traveling at the speed of light and copper. And that actually does make sense if you look at all electromagnetic waves. And so we divide the country in half, basically through the center of South Dakota. And we run two different grids, and they're not going to be in phase. So when you've got power coming from one grid and you need to put it into another grid, you got a problem that it's out of phase. And so we put in motor generator sets along the center of the US that at the rare times where the power imbalance is so great, we need to move power from one place to another, from one grid to the other, we use the motor generators. In Japan, you see this same thing. One of the biggest problems after Fukushima was that half of the emergency generation capability of the country was not set up to where it could switch from 50 hertz to 60 hertz. And there was only a very limited connection to do the conversion between the 50 hertz grid and the 60 hertz grid. That's something that has been worked on and improved there. All right, thing is, that's really only used for big amounts of power. Most of what you're working on, if you're doing a localized grid, you're doing a deployment, you're doing a single base running off of a standby power plant, most of your rectification is going to be solid state. Now, we're not going to go into the details of what's inside a solid state system. You had that in school, and it's really not necessary to understand for this, just it exists. And if you recall, the example for how the schematic's done is pretty straightforward. Talking about the way current flows, which is opposite of the direction electron flows, but the math works good either way. So everything by default is in current flow direction. The arrow shows the direction that power can go through a diode. Current trying to go the other direction gets stopped. Now notice we don't say it's going from positive to negative. We're saying which side is more positive. That's going to become important in just a little bit. Now, you can do for a single phase AC system with a single diode, you can make it DC. The thing is, you end up only being able to pass one half of the sine wave. So what you got is a DC current that, like I'd said before, goes from 0 up to a peak and back to 0, and then does nothing for a while, and then goes from 0 up to a peak and back to 0. This is technically a DC load. However, or a DC output. However, it is a DC output that will fry most computer equipment because it'll keep going down through a brownout condition. So by itself, a single diode system on a single phase power is not going to provide you the type of power you need for most of the equipment that you're trying to connect to it in a modern installation. Now, ideally, we want a diode to act like an open circuit when blocking. It should be the same as if you opened a switch or you pulled a chunk of wire out. We'd like it to act like a short circuit when conducting. The thing is, it's a bit more complex in the real world. You will always get back current leakage in a diode when it's blocking. And diodes have a pretty consistent voltage drop while conducting, about 0.7 volts if it's a silicon diode. Then you also have situations where you intentionally want it to leak, or more importantly, break down, and those are Zener diodes. And a Zener diode, once your power gets beyond a certain level, it lets it flow backwards in there. And this is used as a safety device in many systems. And it is also used in some older control systems as a timing device. And we'll get into that a bit more later. This is what you're used to seeing for a diode. This is what you had in your first EE classes. It's a small little cylinder. It's only good for about 5 amps. And the reason is you don't have a way to get the excess heat out of it. The carrying capacity of it's based basically on the volume of the diode, but the heat dissipation is based off of the outer surface. And on a cylinder, your outer surface increases a lot slower than your internal volume. So the problem is getting rid of the heat. Well, one way you get rid of heat is you add a heat sink. Now, the thing that I want you to keep in mind is you're going to be working on equipment from a large number of manufacturers at a lot of different ages. And it's been through a lot of stuff to get where you need it. So when we put a heat sink on, it's something with usually aluminum because it can radiate the heat away from the diode. But unfortunately, the stuff that insulates from electricity usually is also a good insulation for heat flow. So as thin as possible of an insulation is used between the heat sink and one side of the diode. And over time, this insulation breaks down, especially if, despite having the fins on it, the heat dissipation wasn't sufficient. If you take something like this on a machine that's in Camp Lemonnier in Djibouti, where it's above 100 for multiple days of the year and it stays very hot all the time, the insulation's most likely breaking down, which means eventually all of that aluminum becomes part of the circuit, which means it's not only hot physically, it's hot electrically. And it's another good way for you to get, if you're lucky, only a nasty shot. It goes even further. You will see some installations, especially on bigger electric machines, where the diodes are actually screwed into the frame of the machine to make the heat sink. And the same problem applies. This can become especially critical if you're doing anything along with your NATO allies, and they got some of the French electric powered equipment there, because this has been in the past fairly common among them. And again, it's a good way to get exposed to current when you're not expecting it. Here's a way you're fairly common to see it: 4 diodes in one housing. One of the things you're going to see a lot later in this course is something like this: assembly of 6 diodes, 3 in one orientation, 3 in the other. This is going to become important in how your generators are actually controlled and regulated, because they're a bit of a preview on it. There's actually 3 different generation processes occurring on your standard generator, and in between them, we're needing to convert power back and forth between AC and DC. So we talked about the single phase. Now, on a single phase half wave, we're only getting about 45% of the RMS voltage measurement becoming a DC voltage measurement for the load. We can do a full wave instead and get about 90% of it. Why only 90%? Well, remember that 0.7 volts drop across each diode? That adds up. And here's where talking about more positive instead of positive and negative makes a difference. Because let's look at how the power goes through. Let's say this is positive to begin with. Comes to this node. Well, at this node, it tries to go both ways, right? Well, it can't go that way. It's blocked, so it goes through this diode. Gets to this node. Can go both ways, but can't go through this diode, so it goes here. Positive side of the load. But then negative comes back, and it hits here. According to the diagram there, it should be able to go both ways. So why doesn't it go this way? Well, that's where we talked about more positive. Okay, if this was 120 volts here, that wire running to the diode has very little drop, so it's about 120 volts here. But here we've got at least 0.7 volt drop and almost certainly a hell of a lot more drop through your load. So that means that this is something under 120. So it's less positive than here, which means it'll go back through this way. And everything runs through in reverse when this becomes the positive one. Now, we're looking at three-phase. Well, what if you want to do three-phase, but want to do a single diode for each phase? Well, to do that, you need a Y connection, because the only way that the power could come back, since it'll be blocked by the diode on each phase, is to come back through the neutral. That's okay, but again, you're only looking at a little over 67.5% of the power is actually available to your DC load, and we can do better than that. And if you look at how does the DC power look, it basically looks like the top part of our three-phase sine wave. We're running along the bumps on the top. We never go to zero, but we do have quite a bit of dip. This can still be a problem if you're running microcontroller loads off of this, because depending on how much drop you got on the lines going from your generator to your electronic equipment, this can drop into the brownout range for them. This is what's preferred. This is a three-phase full wave rectifier. It's got 6 diodes on it. Kind of makes sense why that disc we saw earlier had 6 diodes on it that we talked about, and how the generator is making DC voltage for its internal circuits. Now, the interesting thing on this is you can do it off a delta connection. You don't need a Y and a neutral, because when this is the highest voltage, the voltage on the other 2 lines is less, which means there's always a return path for the load to come through. Here's the interesting part. We're looking at 1.35 and change of the amount of voltage that came in. We're getting 35% more voltage at the DC load. Sounds like we're making something out of nothing. Actually, it's not the case. And this comes into, again, being lazy and wanting a single voltage number to talk about something that's really alternating. Because if you ran this on a scope, what you'd see is the DC has these little humps. And these little humps here never go down very far compared to what the peak voltage is in the sine waves. Remember, RMS was a form of averaging. It's saying, what if you had a full sine wave, what would be 70.7% of it? Well, we never get down to that 70.7 line on any of these curves. So the resulting voltage measured with a multimeter is going to read 35% more than what our AC voltage read coming into it. Are we actually getting more out? No. It's just how the averaging is done to get RMS. Remember, voltage and current actually are instantaneous. RMS is just a convenient lie that makes the calculations easier. All right, so here's the thing. Diodes go in one direction but not another, but they have no way of controlling the current through them. If we want control, we need to do something different. And while we could go all the way to a transistor for it, what we really do in most of the stuff you work with is we go to what's called a thyristor or a silicon-controlled rectifier. This is an interesting little piece of kit. It's like a diode with an on switch, but it really is an on switch and not an on-off switch. So what do I mean by that? Well, for those of you that are in an office or an official building to do this, take a look over at the door. The door is closed. It's got a hydraulic system to pull the door back closed, and it's got a latch on it. That latch has either a lever or a push bar on it. Now, in the room that you're in, if the fire alarm goes out and you and your buddies got to get out of there, the first one of you to the door hits that lever or hits that bar. If he doesn't hit that bar, the door's not going to swing open. But as soon as he hits that lever and the door opens, the next guy through him doesn't have to hit the lever again. He just pushes through. And as long as there's bodies moving through that door, it stays open. As soon as the last guy goes through, the hydraulics on the door close it again and it latches. And now that it's latched, no one else can go out. And at the same course, if someone tried to come in on that door, if we ignore the latch on the outside, they got no way of getting in. They come up to the door, their motion at the door swings it closed, they can't get it in. If the door is latched, they also can't get in. That's the way an SCR works. We want the power to flow through in the direction of the current, just like a diode. But then here, we have got the trigger signal, and that's our door latch. So why would we want this? Well, take a look at what happened. If we got an alternating current coming from the grid or coming from a generator that's running, and we run it through a full bridge rectifier. All right, now you got a DC voltage like this. If you send a pulse through and use that to turn on an SCR, what you'd see is absolutely no power on the outside SCR. Well, almost nothing, because there's always leakage. Then all of a sudden, boom, there it is. And you'd see it until the power on the load coming in goes to zero. As soon as it hits zero, boom, the thyristor stops letting power through. And it won't let any more through until something hits the gate again. Boom. Why is this important? Control systems. All right, when you're taking a look at older power plants, okay, right now there's a big concern with EM pulses and how that's going to affect power on your bases. All of your standby power plants end up having to be put into a Faraday cage. Having helped design these, I can tell you right now it's a pain in the ass, because you need a large amount of air coming in for both combustion on the engine and for running through radiators for cooling. You also need exhaust gases to get out. Well, all of those big holes need to have very tight grids of basically welded together metal tubes in order to make a ground that runs through the whole thing. This is what keeps the EM pulse from coming in, hitting that, and actually shorting out the electronics that control the generator and the engine. And the problem with this is, if there is a grounding issue, if there's corrosion between the grill that's over the air exhaust and the rest of the metal building frame, if there is a grounding jumper that came loose, you don't have a full cage anymore. And that means then that EM pulse can get in and fry stuff. So you got to spend a lot of maintenance time making sure that corrosion and physical flexing from heating and cooling and a dozen other things haven't ended up causing your grounding to be incomplete. And even if you do that job correctly, all it takes is for the door to be open at the time the EM pulse hits, because someone's coming into or going out of the building, and the whole thing is fried. Now, older generator systems, and in some of the locations that you're at, you will find older like Cat 3600s, the MTU equivalent or the Cummings equivalent of them. They have control systems that work with relays, thyristors, and Zener diodes. And the way that ends up working is you got a sensor reading something, temperature or voltage or whatever, and it's being used to charge up a capacitor. When that capacitor gets to a certain voltage, then a Zener diode dumps it. That's being used to create the gate pulse current. And basically, then at the control side, you're hooked up, getting the same AC power, getting the same rectification. It's building up another capacitor, but instead of having a Zener diode time window drop, the gate current pulse that came from the Zener diode at the sensor triggering and letting go is what sends out the information to release that capacitor. What this ends up giving you is that you now have a way to do a timed load. You have a way to vary the amount of power coming into your control system based off of the same alternating current being used as a timer for both ends. And the reason this is better in risky environments is that thyristors and SCRs are a lot bigger. They have a lot bigger layers in them on their equipment than the really, really tiny transistor traces that are in a modern microcontroller. So these big, bulky, old systems can handle a lot bigger EM pulse before failing. Now, that's not to say it's going to be completely safe, but you will find that in many places where you're doing prime power there, besides for backup power, your backup plant will have modern equipment like Cat C280s or 3520s in them, and have all the modern electronics to do everything quick and efficient as possible. And then you're going to find your prime power plant has much older equipment, Fairbanks Morris, Cat 3600s, Wattzillas, that use a control system like this. And the reason for that is you want as much as possible to not have to go to that backup power plant. And so your main power plant is designed to be as robust as possible. All right, so let's get a little more into resistance. We know that increasing the resistance reduces the current flow. All right, so for a resistor, that's all it does. If you look at it discretely or look at it in RMS, it's the same thing. The voltage wave and the current wave are at the same height. Well, not the same height, but they're in sync. So here, both the current and resistance is zero, and the amount of power you make there is zero. Here, both the current and the voltage are at max, and the max power is made. And how that works out then, as long as everything stays in sync like this, taking RMS voltage times RMS current is going to give you the RMS power that's really available to come out the back end and use for your equipment. We'll get into later cases where this is not true. All right, automatic voltage regulators. This is going to be an important part of your generator. It's something that's going to be discussed more tomorrow. One of the things that they use is resistance to protect the regulators from overcurrent. Now, if you are using lamps or amps out in the field, Cummings designed all of those, had the voltage regulators on them, they're good to go as they are. If you buy rental equipment or rent rental equipment from a local source, and you get a Caterpillar or Eaton or anyone else on a standard unit from a rental place, it will have a regulator that's designed for it. However, you will get into situations where either the equipment you're using is so old the regulator is not available, or you're in a location where getting a correct regulator there is hard. Fortunately, there are general power equipment suppliers that have voltage regulators made by Eaton or Schneider or many other people that can be sized for whatever machine you have. And one of the things you need to understand on that is how much resistance there is in the coil the voltage regulator attaches to. So if you have a voltage regulator of a maximum output voltage of 100 volts DC and a maximum current carrying capacity of 5 amps, how much resistance do you need in the coil it's attaching to so that you don't blow this thing up when you use it to repair your downed genset? Well, E equals IR, so you swing that around. Resistance is basically voltage divided by current. So the resistance for 100 volts and 5 amps means you need to have a coil that's at least 20 ohms resistance. If you try to hook this particular voltage regulator onto a coil that has less than 20 ohms resistance, what's going to happen is when you power it up and start putting a load on the machine, you're going to fry the voltage regulator. All right. So resistance is like friction. It creates heat within a conductor when the current flows through it. And the amount of heat generated is a function of the amount of current flowing through the conductor. The resistance of the conductor changes with temperature. Now, for copper, we know that it changes by 0.393% per degree C. That's not much, but it's there. So if we know the cold resistance of the copper, we can use its hot resistance to determine what the temperature is. Okay, this is termed temperature rise. And the measurement by looking at the amount of resistance before and after an event occurs, that's called rise by resistance. This is something we do when we design a new generator. Okay, we've worked out the math for it, but to actually test it, we take a generator, whole gen set, we hook it up to the maximum rated load it's supposed to be, and we fire it up. And we run it until the temperature measurements we get everywhere on the generator are stable. We call that a thermally saturated condition. Now we know the ambient temperature that we're at for the test, and we measured the resistance of the wiring in the windings of the generator at that temperature. When we've thermally saturated, we shut it down and we quickly disconnect it from the load, and then we measure the resistance of the generator while it's still hot. This gives us the rise by resistance. And the reason why that's important is when we sell you something, any insulation that's on a generator has a certain total temperature that it can take before it breaks down quickly, what's called crosslink temperature. If you've ever taken a really old power connector, like for an old Kindle book or something like that, and try to plug your modern high charge rate phone in to charge it, you find after a while that cable starts getting brown and cracking and breaking up. That's because the amount of current flowing through to charge a modern phone is so much that the wire is getting too hot. So the insulator is getting too hot and it's cross-linking. This can legitimately happen in a generator set. And when it does, things go bad really quick. You start breaking down the insulation, you start getting shorts between windings, phases, and case ground, and all of a sudden you got what's called a ring of fire as the entire air between the stator and rotor of the generator all ignites at once into a plasma. And soon after that, the lights go out in the facility. Now, it doesn't have to get to this critical stage because even if you're running below the crosslink temperature, every 10 degrees Celsius that you go up in the temperature in the system, you actually cut the insulation life in half. Generator insulation is designed to last 20,000 to 40,000 hours. You run it hot all the time, its life's going to get shorter. Again, this is especially critical when you're in some place like Dubai, because not only do you got the rise in temperature from the load you're putting on, but it's rise over the ambient. So the temperature coming in makes a big difference. And so you must understand what the temperature ranges are for your genset and what the ambient temperatures are that you're working in to tell whether all of the load the commander's insisting that you put on this genset can actually be run continuously without the machine failing on them. But the problem is measuring rise by resistance by measuring the resistance of the coils in the generator doesn't work while the machine's running. You can't measure resistance in an active circuit. You need an inactive circuit because resistance is a physical property, not an electrical flow property. So for that, we have RTDs, resistance temperature device, or resistance temperature detector. What these are is basically a very precise thickness and length, the copper wire, that has some insulation around it, and then it's jammed into the windings of the generator or any place else that you're trying to measure temperature. And the thing is, it's a separate circuit because the insulation is blocking it from the rest of the coil. So if we put a known current into it or a known voltage into it, we can then read the resulting voltage or current back. Basically, an RTD is connected to a multimeter, but the multimeter is calibrated to, instead of reading ohms resistance, it's calibrated to read temperature. And it can do that because there are industry standards for what the resistance of an RTD should be at a given temperature. And we know that value, and our meter is set up to scale from that value. So a copper RTD reads 10 ohms at 25 degrees Celsius. A nickel one reads 120 ohms at 0 Celsius. Platinum reads 100 ohms at 0 Celsius. And setting that on the gauge then tells it what scaling factor it should use and what starting point it should use to give you a temperature reading as an output. So, capacitors. All right, principal characteristic of a capacitor is it's storing electrons. The movement of the electrons is what's making your electric current. So, capacitor basically is two plates. They could be wound around each other in a cylinder, they could be flat, doesn't really matter. It's basically two parallel surfaces. Now, the thing is, when you look at them, they should block current flow the same as opening a switch. That's not exactly so. If you close the switch in that last example, the current flow goes up really fast as all the electrons go rushing around and they hit the capacitor. It's like going into a conference room or going into a train car. And the thing is, electrons don't like being around each other. They'd like to be as far away from other electrons as possible. So as they go into the capacitor, they go to the far ends of the plate. When those far ends are filled up, they start filling the middle, and they try to spread it out so that there is the maximum amount of space between each electron in there. And the thing that you get is when they're in as close as they can be with the amount of voltage trying to push them, no more flow occurs. Think of this like a Japanese train being filled up by people going to or from work. Okay, the number of conductors on the outside pushing determines how many people they can squeeze into that car. And that's the same thing that happens with a capacitor. The electrons push in on one side because everything balances out. Electrons are pulled away from the other side. The more voltage we got, the more it goes in. Here's the thing, though. When we close that circuit, those electrons are all still sitting there, which means it's retaining its charge. If you've looked at the plug-in for your laptop and the little green light on it, when you've unplugged that from the wall, the light doesn't go out right away. It slowly drains down, and that's because the capacitors in the system are still holding power. And while it's not that big a deal if you touch the ends of the plug on your little power supply for your laptop, it can be a big thing when you're looking at the capacitors on a control system. So here's the important thing. Your technicians will most likely have with them not only a multimeter to measure the amount of voltage potential across capacitors and everything else, they'll probably carry something like this: a very large capacity 1 kilo ohm resistor with the leads on it being insulated down to just the ends. They touch this to the prongs on the capacitor to allow it to discharge. Now, why are we using this instead of just a screwdriver? Well, the thing is, a screwdriver across there has almost no resistance, which means the current flow is going to be very, very high, which means it's going to get very hot, and it's also going to try to arc. So it is downright dangerous to short out capacitors with a screwdriver. If one of your technicians is doing it with a screwdriver, encourage him to use a different method. It's better than nothing, but it is much better to do a slow, controlled discharge of this. Always assume every capacitor you run onto still has a charge until you prove otherwise. All right, so like we said about the Japanese train example, if we up the voltage after capacitor is charged, we can shove more electrons in. If we decrease the voltage, we can't hold as many electrons in, and some of them flow back out. So what you could say is that capacitor, by holding on to electrons, is opposing a change in voltage. This is why you have the capacitor part of a filtering circuit. It slows down the change in voltage. It's important to understand that what we're slowing down is the change in voltage with this. So we store it, it changes the pressure on the rest of the system. That's the voltage. Hindrance to current flow is termed capacitive reactance and given the symbol X sub C. Since capacitors oppose a change in voltage, they'll delay the voltage wave relative to the sine wave if you put them in an AC system. Now, if we could make something that was a pure capacitor, had no resistance in it at all, it would offset the voltage by exactly 90 degrees. So here's an example of that idealized one. Now, the thing I want you to look at is take a look at these 0 points. All right, here the voltage is 0, but the current is high. Here, the current is 0, the voltage is high. Voltage 0, current high, and keeps going through it. At each of these points, the amount of power produced is 0 because it's volts times amps, and instantaneously volts times amps at that instant is 0. Meanwhile, over here, you've got a voltage and an amperage, but you notice that the total you get from the two is less than you'd get if these two sine waves were synced up. So you're actually getting less power from a circuit that has a capacitor in it than you're getting from a circuit that does not have one in it. All right, magnets. Here's one of those nice little lies that we tell to make things easier to educate. We talk about lines of flux like they are physical things. In reality, lines of flux are like the lines on a topographic map. They're showing equal potential. The reason that we see lines of flux with iron filings when we sprinkle them over a piece of paper set over a magnet is because the iron filings are long and narrow, and they're light enough that the magnetic field can move them around. And the filings want to stay at an equal magnetic potential along their entire length. So they orient basically to where the potential along their length is as close to equal as possible, which makes them just like the lines in a topo map. So instead of talking about lines of flux that we're cutting, we should be talking about going upslope or downslope of a magnetic field. But force of habit, and it is kind of easy to picture more lines of flux, steeper slopes. So cutting lines of flux is what we're going to talk about. Greatest concentration of flux is at the poles. The more lines, the closer together they are for a given size of filing that you're using to make the image, the more powerful the magnet is. So you got strength of field, you got orientations of the poles. Like poles repel each other, unlike poles attract each other. Thing is, if you take a piece of hard steel or a piece of iron, you can magnetize it. In fact, all it takes is take a piece of iron pipe, point it towards magnetic north, and whack it real hard with a ball peen hammer. it will become a magnet. And the thing is, it will remain a magnet even when you take it into a different orientation. This is called retentivity. Now, for the most part, in a generator, you don't want retentivity. The only time you want it is you will see that a lot of your lower cost generators, especially in the lower power ranges, are using what's called self-excited. And you'll learn more what that means later. But basically, you need a magnetic field of some sort to get a generator to start. And instead of having a permanent magnet sitting somewhere spinning or anything else like that, it uses retentivity of a magnetic field in the core of the generator from the last time it ran to start it up again. Now, you only want a really, really small bit of it, as we'll see in just a bit, but that's needed to actually get a self-excited generator to start. Thing is, once magnetized, you can't control a permanent magnet. It is what it is. It doesn't need a source of energy. Well, here's a guy you probably haven't heard of. I call him the dull Dane, Hans Olstead. He observed that when electric current flows through a conductor, a magnetic field is created around the conductor. The thing is, he didn't mean to. He was convinced this didn't exist, and so he did the one thing you never do. He set up a demonstration in front of his students at the university he was teaching at one day without trying it himself beforehand. And what he did was this. He took a battery pile, he hooked a wire up to it, and he brought a compass near it. And his argument was, far away from it, the compass is pointing north. And if electricity made a magnetic field, then he should be able to get the compass to change direction as he approached the wire. And he said it wouldn't. And then he walked towards the wire, and it did. And what he found, quite to his embarrassment, is he found excitation. And what he found is that this field occurs around a wire. And you can apply, as you remember back from school, the right-hand rule. The direction that is north-facing is the direction that your fingers point if you have your thumb running around along the wire in the direction the current's flowing. You wrap more coils of wire around, the field gets stronger. If you have those coils and look at it the other way, doing the right-hand rule on any part of those coils shows that your fingers keep overlapping down the center. That makes the center of a coil of wire act stronger. It has flux lines closer together, which means you can pretty much right-hand rule the whole coil as one and say there's going to be a north pole and a south pole out of this coil at the opposite ends of it. All right, if you want to maintain constant polarity in electromagnet, the current's got to be direct current. Alternating current will cause the polarity to reverse, go back and forth. Big thing if you're trying to do a electromagnet to lift items. So that's why you're going to see a lot of DC power supplies or motor generator sets to convert AC to DC at ports and at scrap yards where an electromagnet is being used to move cargo. Because remember, to go to alternate polarity, it's got to go through zero polarity. And while it's at zero polarity, whatever loads on there starts to drop. And since the amount of magnetic force varies with the square of distance, even if it drops only a little bit, the amount of force needed to catch it again is much more than what was needed to hold it there in the first place. Which is why these need DC current, because otherwise the amount of stuff you pick up, you keep dropping it as you're carrying it around. You talk about electromotive force, there's also magnetomotive force. It's the product of the number of turns conductor times the current flow in the coil. And here's the thing, you can make a 10-turn coil carrying 50 amps, or you can make a 500-turn coil carrying 1 amp. And depending on what type of motor or generator you're doing, you might do one or the other. The thing with running a lot of turns at a lower amperage is it's a little bit safer, but more importantly, it's cheaper to manufacture because it's a lot easier to bend small wires. So most random wound generators and random wound motors, they use a lot of a very thin wire to make them because it's cheaper to manufacture them. When you get into really big generators, you'll find components on it that'll be talked about later in the generator section, where they're doing fewer turns and using actual bars instead of wires and carrying bigger current. And in that case, since you're having to manually assemble something that takes some really big tools to bend anyway, you want to minimize the number of them that you're doing. All right, magnetic permeability. That's how easy is it for the flux lines to pass through the space? How easy can we put a magnetic field in it? Turns out soft iron is more permeable than air. Okay, so you see coils with an iron core in it, it's because that causes the magnetic fields to focus more in the middle. Now, do we want higher intensivity on this iron core? No, because whether we're making an electromagnet to lift something or we're using it as part of a generator design, then we're going to be alternating the current in it. We want that when we kill the power or reverse the polarity, it changes right then and doesn't retain the previous magnetism. Now, if I want to make an electric car, could I use aluminum instead of iron in the motors to save weight? You could actually make a motor that doesn't have any iron in it, but the problem is this: the retentivity is low in both the iron and the aluminum, but the permeability is so much higher in iron that the difference in permeability is greater than the difference in weight between aluminum and iron. So while you could make a really, really big motor that's all aluminum instead of iron, it would weigh more than the much smaller motor that you could make that had an iron core on it. Thing is, no matter how many conductors you got pushing electrons in, no matter how steep of a slope you try to make in the magnetic field, there is a limit. That limit is called saturation. Once you get to saturation, it doesn't matter how much more power you put in, you are not going to be able to get any more changes in the device. In a magnetic field, if it's magnetically saturated, increasing the current in the coils creating the magnetic field is not going to give you more magnetic force. This makes a physical limit on how small you can make an electric motor of a certain power, how small you can make a generator of it. There's a lot of tricks that can be made that if you're not needing it to last more than one mission, that you can make it a lot smaller than the standard stuff that you're using for your base or for rental powers. But even with that, there is a limit. All right, so thing is, everyone knows microfaraday instead of Olmsted. And the reason is because over a century after Olmsted, Faraday was doing the same thing, but took the next logical question. If a magnetic field can be created by electricity, can electricity be created by a magnetic field? And what he found is that as long as a conductor is moving through a magnetic field, it will create power. And he found that the number of turns of the coil that's being used to pick it up matters, and the number of lines of magnetic flux, how fast the magnetic field is varying, matters. In other words, it was the stuff Olmsted had discovered more than a century prior and didn't follow through on. And here's the thing: all that stuff you see on YouTube where they set up a magnet then and get power from it continually, well, you already knew it from your schooling. That doesn't work. You need to have a relative motion between the conductor and the magnetic field, or you don't generate power. So if we consider a coil of a fixed number of turns, the voltage induced in the coil is strictly a function of the number of flux lines cut per second. So in other words, how strong is the magnet and how fast is the relative motion between the magnet and the copper? If the strength of the field is constant, varying the speed will change the voltage. All right. So that's why we have voltage regulators. But there's going to be more to it than this, because as we'll see later, this difference in there is also going to cause fields to build up and collapse. And that collapsing is the same as having the magnet move. And that's going to come into play in just a bit. So inductor, we've already talked about, it's a coil of wire. It may have an iron core, it may not. transformer is basically a couple of inductors, 2 windings or more around the same core. Generators are basically several windings around iron steel cores. We are using inductance everywhere through the rest of this course, and they store energy. But unlike a capacitor where it's easy to say they stuff electrons into a place and push them in, and that's how it's stored, the power is actually stored in an inductor in the field, the magnetic field around the coils. All right, so if we increase or decrease the current flow, we increase or decrease the magnetic field about the conductor. And we learned that determining the voltage induced in a coil, big thing is the change in the flux lines per second. How fast do those flux lines go past? Well, that's the thing. If we apply an AC voltage, we're building up flux lines and expanding out of field, and then we're collapsing it down to 0, which means the flux lines are moving again relative to the wire coming in, and then they're going out in the opposite direction. So that means that we're repeating this back and forth. We are making the flux lines move just by having an alternating current in the wire. But you see, the thing is, the wire, that means the wire then is in a moving magnetic field, and we are inducing another electric flow into the wire. This voltage that we're putting in opposes the direction of the current flow in the wire. It's basically the collapsing field from the other half of the cycle fighting the field trying to be made in this half. So an inductor hinders current flow, just like a capacitor hinders voltage flow. This is called inductive reactance, and we give it the symbol H sub L then. So capacitor reactance is X sub C, inductive reactance is X sub L. And the thing is, it's a resistance. Each of these reactances is acts like a resistance in that it hinders flow, but it's not really a resistance, because see, an actual resistance puts power out in the heat. But since it hinders flow the same as a resistance, we just measure it in the same way, ohms. So the two things to this opposition, the induced voltage is caused by the current wave, causes the current wave to lag the voltage wave, and the inductive reactance is dependent on the frequency. If you change the frequency, the ohms of inductive resistance change. And the same is true of inductive capacitance. What that means is if you do a higher frequency, a smaller inductor or capacitor will do the same job. Now you see why on the flight line they're using this. 400 hertz means you can do a much smaller inductor with its iron core and get the same results in any radio equipment or radar equipment or anything else in an aircraft. That makes a weight savings. And since both the inductor and the capacitors are smaller, it's a space savings. So this is why you have 400 hertz in avionics systems. And since radar systems, first of all, were designed initially by avionics manufacturers, and so they did what they're used to, you also got the problem that the amount of inductance and capacitance that are needed in these systems is huge. And so to make something that actually can fit in a reasonable sized building or on a reasonable sized trailer, 400 hertz lets you shrink down all of these major power components. Again, it's a 90-degree offset if we could make a perfect inductor, but notice that it's in the opposite direction of the direction the capacitive inductance is. In this case, here's the voltage, here's the current. The current is lagging the voltage. So frequency makes a difference. Inductors and capacitors have opposite effects on an AC circuit. It's entirely possible to have one cancel out the other. So one of the things that you're looking at is these things are not dissipating power like resistance. It's the shift that's making it that power that should be available isn't there because the voltage or the current is being shifted in time. Now, this is important because it means your engine doesn't have to be bigger to make up for this phase shift. But what do we want to do when we add these together to get the math to work? Well, since they're all affected by, we want to add them together, we want to make impedance. That's the amount of resistance and the amount of reactance in a circuit. Well, we can't just add them together because XL and XC cancel each other out. We can't just subtract XC from XL because what happens if XC is larger than XL? What happens if it's so much larger that's even larger than resistance? We end up with a negative impedance value, and that's not possible. We can't get more power out than what we put in. So we basically do root mean square again. Resistance squared, the difference in inductance and capacitance squared, so it becomes a positive all the time, the square root of it. So AC circuits, we do E equals IZ instead of E equals IR, and we have to understand what frequency they're at so that the calculations actually work right, because Z, since it's including X sub L and X sub C, inductive and capacitive reactance, and both those are affected by frequency. If we don't know the frequency, we can't do the calculation. And that brings us to power factor. And I really hate the foam and beer analogy because it's not really making sense. V times A would be the total power. Remember that if we had actual just resistance, voltage would never cross a 0 point except when amperage does also. And so we would always get the maximum amount of power that's possible from it. But since we do offset because of inductors and capacitors, there is a usable power. Then the amount that we actually get if we added up instantaneously all of these points. And the difference between those two is power factor. It depends on where the two waves match to each other as to what the power factor is. Or to look at it another way, since your double E's and like imaginary axes, here we got leading and lagging power factor. Leading means we've got more capacitance, lagging means we have more inductance. So if we had a capacitive load on it and a resistive load, the result, if we measured these, would be this line here. So the more capacitance we have, which could be by a change in frequency or by changing the size of the capacitor, the further up this would be pushed. And if we had less, the closer to 0 it'd be. It can be the same thing with an inductor. You can have both in the circuit at the same time, and if they're not at exactly the same amount, you end up with a resultant. Now here's the thing, if we look at this, it's a right triangle, right? And this line here, the total load of volt times amps, it's basically swinging out a circle depending on how you vary the amount of inductance, the amount of capacitance, which means if you zoom in, since this length is always the same to swing out the circle, this length is the length that gets shorter or longer. This gap here between where the real power is at and where the circle arc is for the total power, that's your power factor. That's all that it is. It's not foam and beer, it's nothing magical. It's just what happens when the fictitious RMS voltage and amps we're using don't match up with the reality of what the instantaneous power we can make from out of phase sine waves. All right, quick thing on power and work, and then we're done. SI unit for power is watts. It's named after James Watt, who ironically is the person that came up with the measurement horsepower. All right, the thing is, nice thing about SI units is we can use it to talk about either mechanical power or electrical power. Thing is, you're going to have to keep it straight in your calculations which one's which. So we put this little M for mechanical or E for electrical. Now, the way you're seeing it here is the default standard for how to do it. Kilowatts mechanical, kilowatts electrical. However, you're not going to see it in all literature the same way. For companies that started out as engine manufacturers, this makes no sense. Because when we talk about the power that's coming out the back end of an engine, we talk about brake horsepower. So when we converted to using SI, we talked about brake kilowatts. Well, if we're talking about any other type of mechanical power besides for brake, it should be the same way, right? Total mechanical power should have been mechanical kilowatts. So from companies such as Caterpillar and from, I believe, Cummins also, you'll see MKW and EKW instead of KWM, KWE. Thing is, means the exact same thing, whether you put the M in front or behind of the kilowatts. So power in an electrical circuit is voltage times current, easy as pie. Except, of course, we're doing AC, so it's power factor, but easy as P didn't really flow off the tongue as good. Ohm's law said that E equals IR, so we could use that to substitute, and we could say that the power is related to the current squared times the resistance. Or you could say it's equal to the voltage squared times the resistance and get the same thing. So if current's directly proportional to voltage, E will vary in direct proportion to the change in voltage, right? So power in an electrical circuit is directly proportional to the square of either the current or the voltage. And it will change with the square of it. No, what's that mean? Say you got a voltage across the circuit and it's dropping from 480 volts to 456 volts, drop of 5%. All right, so 100%, it dropped 5% means that you got 95% of the voltage. Or the other way to write that is 0.95 per unit. Well, since the power is related to the square of the voltage, that means you got 0.95 squared or 0.9 per unit, which means the power you're getting is only 90%. So a reduction of 5% in voltage across the circuit will result in a reduction of power demand on the circuit of 10%. But look at it the other way. If you have more resistance in your lines because you're doing a remote operation and you're running lines from your portable power to where your load's at, those lines are a lot of resistance and they only come in standard lengths. So you could end up having a lot of cable that isn't really doing much except causing resistance and dropping the voltage at the other end of the circuit. So what happens on that then is if you still need 480 at the other end, but you're measuring only 456 at the end, your generator's voltage regulator has a function to allow you to turn up the power to get back to having 480 at the other end. But the problem with that is when you go up, you got the same problem as when you go down. You increase the power 5% or the voltage 5% to get it up to where the load needs it. Then after going through all that resistance, it means you increase the power you're needing by 10%. That means that your engine is having to put out 10% more power, which means it's running more fuel, which means your refuel times are going to be longer. It also means your generator is putting out a greater load, getting hotter, and it's not going to last as long. All right, well, besides for power, there's work, which is just power times time. And the thing is, as far as electricity is concerned, you'd think 1 kilowatt times 1 hour or 60 kilowatts times 1 minute will both equal 1 kilowatt hour. This is true, and this is why you got the big surge now and having instantaneous water heaters. And while the circuits inside the heaters are designed to take the wattage rate that you're running into it, your cables running to it are not necessarily designed that way. And that's why you got to be careful that if you're sizing something that's using a lot of wattage, that you've got the rest of the cabling running to it sized correctly. Because otherwise the cabling is going to get very hot and you will end up using more power, plus create a fire hazard. All right, last thing on here. We want to figure out how big of a generator you need, how much power you need, how size of an engine. Well, engine power is usually measured in brake power. That's the amount of power that in the factory, when they hook the engine up to a pony brake and run it the first time, how much power it puts out. Well, in the factory, we don't have the radiator hooked up, so This brake power is the power before taking out the power needed for a radiator. Now, if you're running on a ship with a keel cooler, doesn't matter. Brake power and output power mechanical are the same. But if you're doing anything on land or you're doing an emergency aux generator on a ship, you've got to power a fan. So flywheel power is the power that's left to turn the generator after any parasitic, such as a radiator, is off of it. And then a generator itself has an efficiency loss. A generator on a really cheap system will be 90% efficient. Almost everything that you're going to get on a military contract and most everything that you're going to get as a rental unit is going to be around 95% efficient. So how much power are you getting out the back end? We take the brake kilowatt power of the engine, we minus whatever power is on the fan, we take it times the efficiency of the generator, that gives us the power out the back. So you got a Caterpillar C18 engine, it's putting out 600 horsepower. It's got a fan needed to cool it, takes up 22 kilowatts. The generator we stick on it is a little over 95% efficient at full power. You got a 550 kilowatt max power you can get out the back end. Now, this is different if you don't have the radiators on the machine. Again, for the example, going out to Camp Lemonnier, we don't want all that air running through the inside of the power plant, so we put remote radiators. Instead of driving them by mechanical link on the fan, they're driven by an electric motor out on the fan, which means this piece here is gone, but then the EKW you get coming out the back end, you got to go and subtract the EKW used to run the electric fans because they get priority pulling power from the circuit. But this is the basic setup for understanding how mechanical power relates to electrical output, and that is the last of the basics on electricity. So next up is going to be basics on the prime mover or the engine system. Are there any questions?
And this is just a reminder that if you have any questions, you can go ahead and enter those into the chat box or just turn on your mic. Again, this session, I mean, we kind of flew through it, but it was basically mostly on, electricity that will only be dealing with basic electricity that will only deal with power generation. So that's why I was a little quick. If you have any additional questions, you can send them directly to Paul or myself. Paul, if you want to go ahead and type in your information in the chat box.
All right.